So, questions? Okay, so we were doing this last time, and I think I probably called this A, B, and C. So and I believe we had gotten through A implies B. That's right. So on the other hand, we want to show so I'm going to prove that if you have B, then you have A. I will leave the equivalence of A and C to you because it's very similar, right? So that might be good practice. So so we assume in this case, for all B, the Hom sequence 0 to Hom are A into Hom are B into Hom are B C. Splits. So that's our assumption. We need to show that the original exact sequence splits. So to this end, let, because after all, I can pick and choose, right? So let's let D equal C, and let phi from C to D so here what I'm going to do is I'm going to let this be C, C, C. And let phi from C to D be such that G of phi equals what's the G bar of phi? And so notice that, of course, the identity function is an element of Hom RC to C, right? Certainly we got that. And we know that the sequence is split, so in particular, exact. So this is onto. So there must be some phi from C to B, something in here, such that G bar of phi goes to the identity of C, right? And this is G of phi, right? Because that's what the induced map goes for the covariant Hom. So so if you look at the sequence 0, A, B, C, by the way, we already know that this is exact from our previous theorem, right? Because this is split exact means in particular that this is exact, which means that that is exact. But what else do we have now? We now have that there is a phi such that G phi is the identity on C. So G is onto and splits. So since this splits, this short exact sequence here splits. So as I said before, just the fact that this is short, just the fact that this is exact means that this is exact, but now we have this map that goes phi back from C back to B, such the composition is the identity. And of course, this means that G has to be onto And you got your splitting. Everybody okay with that? Now let's kind of mix in this notion about projectives and injectives. So theorem. And I'm going to do again, I'm going to do a couple of quick theorems in succession, showing you the dual results. Let P be an R module. The following conditions are equivalent. Number one, P is projective. Number two, given if P from B to C is onto so if you have an onto homomorphism of R modules from B to C, then the induced then phi bar from home R PB to home R PC is also onto right, and three, if you have a short exact sequence, and let's pitch for phi, if and I think this last one will answer maybe a question that might have been creeping and crawling around in the back of your brain thinking about this, then is exact. A short exact sequence. Is also exact. I think it's kind of a natural question to ask, right? Because in general, if I just walk up to you on the street and give you some random R module, then this exactness means this is exact for every P, right? But you might ask, well, what does it take to preserve entire exactness? What does it take to actually preserve short exact sequences? And here's your answer. Projectives in the first coordinate preserve short exact sequence. That's what you need, essentially. Now, as you might guess, there's also an analog theorem for injectives. And let's see how that one works. So I'm going to kind of put this up here with good old 674 compare. Let I be an R module. The following equivalent. Number one, I is injective. Any guesses on what the second one's going to be? Okay, there's that. Right. If you have so instead of onto is 1-to-1. So if you have your homomorphism is 1-to-1, then and by the way, which direction do you think we're going here? Right. if actually is onto. Because remember, the sequence reverses, right? Right? And so 3, if oh, 8. If this is a short exact sequence, then so is notice that again, this is the contravariant version. By contra, I mean that it reverses the or reverses the direction of the mouse. So this should be eta bar. And this, I think this sort of helps to explain how it turns the one-to-one here into the onto here. And we actually saw that when we proved our earlier theorems concerning this, because I think I did contravariant before. So let's, since I do like projective, we'll prove 6, 7, 4. So let's go through this. I think these proofs really kind of help see what's going on. Okay, so let's go through this. Okay, so what do we have? We have P is projective. And what we have to do is show if you have a homomorphism from B to C that's onto, then the induced map from homar PB to homar PC is also onto. So let me see if I can deconstruct this. What do we have? We have V to C. This is onto, and this is, I call this phi. And we somehow have to show that the induced map phi bar from homar PB to homar PC is also onto. Well, I'm going to take advantage of this projective thing here. Suppose, let's say, let pitchfork be in home R. Well, actually, let me change the letter here. It's still F and home R. I have to show that that F and homar PC actually comes from something in homar PB. So there's something phi bar of some function from P to B goes to this one, right? Well, let me kind of help the diagram here. So this is kind of a picture of what I've got. Right, I've got P is onto, and I've got this F that goes from P to C. Well, what do we know about P? That's right, P is projected because that's our assumption here. So I don't know much, but there's an H here. Since P is projected, there exists H from P B such that when I do H and then I do phi, this is F. Right. But this is exactly the induced phi bar H. So H in homar PB is such that and then you get. Okay with it? So now I've got 1 implies 2. Let's move this along, see if we can get 2 implies 3. So now what we've got, I think 2 implies 3 is going to be pretty easy. Because what we have here is if this function is onto always, then the induced function from Hom R to Hom R is also onto. So let's see what this gives us. Suppose A, B, C, 0 is a short exact sequence. Well, from previous results, we know all we need is the exactness here to give us the exact. Then 0 into Hom R PA into Hom R PB into Hom R PC is exact. We get this automatically from previous results, where this is, of course, okay. So all we need is this much exactness, and we get this much exactness here. But as this is onto by our hypothesis number 2, we have totally forgot. Okay, so funny. Not too shabby so far. In fact, this is tailor-made. I mean, it's like if you look back at the proof of 1 implies 2, I mean, it was just basically its definition of projective. So this is all coming together nice. Oh, already done that, haven't I? How about 3 implies 1? So given any short exact sequence, we know that the Hom sequence is also short exact. We need to show that P is projective. Right? So the following diagram. We need to show there exists H and P to B such that when you do H, then you do P, you get F. Right. And it looks like what we've got to go on is we've got something about short exact sequences. I don't see any short exact sequences here. Or do I? Let's look closer at my diagram that I need for the projectivity. Of course, what I've got to work with is number 3, which says a bunch of stuff about exact sequences. I don't see, I mean, I see sort of, maybe sort of half of an exact sequence here. Okay, can anybody, how might I expand this to an exact sequence here? There you go. That's such a cheat, right? But there you go. You've got the exact sequence, right? So and this, of course, is just the inclusion map. So it's easy to check that the image of this is precisely equal to the kernel of this just by the way I set it up. So what does this say? The induced sequence is exact. Namely, 0 into Hom R P kernel P into Hom R P B into Hom R. And this is induced by inclusion, and this is induced by. In particular, this last one is onto, right? So what can we do with that? Well, since F is in Hom R P C and P bar is onto, there exists H in Hom R P B such that P bar of A, which is the same thing as VH, is out. So P is. Any questions on that? All right. Let me give you a theorem. This is kind of a functoriality theorem. Basically, what this says is this theorem tells you how Hom behaves with direct sum and direct product, or at least partially tells you this theorem. And obviously, I won't do this in its entirety because part of this is assigned to you. So let's, our ground rules are let A be the family AI, an index in there, and the family DJ, J and J, all the R models. Okay, then we have the following isomorphisms. A Hom R so of course the direct sum of AI is also an R module. How does this interact here? Well, this is isomorphic to Hom. I'm sorry. Hom R AI. So in other words, this is like a little bit of magic here. I think about pulling the direct sum out, but it actually turns into a direct product. In the second chord, it behaves a little bit more like what I think you think it should. That is to say, you look at Hom R A direct product of BJ. This pulls out the way you might think it would pull out. So I believe I'll let you do part A in the homework. Let me just, I'm not even going to do B either completely, but I'll certainly kick you down the road for some details here. So let's go sketch of B. Since the A is kind of homework. But I guess what I want to do is kind of decide this. Oops. I guess what I would really like to do, so you can think about how to finish this off, is I'd like to try to understand how this works. Right? Maybe I need a little help over here. So my input is going to be some F, where F actually goes from A to the direct product of BJ. So my input is this homomorphism that goes from A over here to the direct product of BJ. Now, what does my output have to look like? Well, it's a direct product of a bunch of garbage, right? So it's got to look like this, indexed over J, right? And it's gonna have like, let me call this F sub J, right? Where each Fj is in home or from A to Bj. So somehow, in an intelligent way, I have to take F and assign to it a net or generalized sequence, whatever you want to call it, where all the entries are homomorphisms from A, not to all of the product of BJ, but to a little piece. So how might I do that? How might I get Fj here? That's essentially it, right? One thing that I do know is for the direct product, I have this thing called I wish I had indexed this different. Right. So for any K in this index set J, I can project onto the K factor, right? And I think that's what I want to do to find this Fk. And that is go over here and then drop down to the appropriate coordinate. And this is going to be what I do. And that's the way this is going to work. This should be so capital Phi of F should be which is F and then projection on J, where each pi J is projection on the J factor. Now, see if you can prove that this is an R-modular homomorphism. That's not too difficult. And that this is also 1-to-1 and onto. Right? This one's a little bit stranger, so that's why I gave it to you, because it's got a little bit more fun to it. Okay. Any questions? Okay. questions. Okay, so Eric, you okay? Sure. You looked a little disturbed there. Looked like you saw a ghost up there or something.
I'm not completely understanding, but
Well, so what you do is this thing right here is the homomorphism from A to the direct product, right? So your input is A and your output is a sequence of things. This is just a homomorphism that goes from here to here. That's what F is. What I need to do is, in an intelligent way, get a collection of homomorphisms that go from A, not to the direct product of this, but to each individual one, right? And so how do I tell this what to do? Well, let me simplify this a little bit just by thinking this is like F1, F2, or whatever, right? So if you have the original F goes from if that's your F, then your output in these FIs, and what are the FIs? Well, for example, F1 is just a projection on the B1. Right, so you do F and then you project out to B1. So the way you get F1 is you just read the first coordinate of what F does. The way you get F2 is you read the second coordinate of what F does, and so forth and so on. Right here, I've got it indexed by a much bigger set, but that's exactly what this means. Do F, and then this says read the J coordinate. That's essentially what it means. And each of these, of course, are separate functions. Everybody okay? Is that a little better? Okay, good. Okay, so talking about Hom, right? So we've talked about Hom a little bit. We see how it behaves with, well, direct sum in the first coordinate, direct product in the second coordinate. And now I'm going to do something that it's almost like you're going to think I'm having a stroke, right? Because I started doing this tensor part, so what freaked out, you're doing something different. But actually, in a very intimate way, tensor product and Hom are related. And in fact, on the next homework, I'm going to give you a problem. I will give you the theorem here that sort of shows how you compare these. In a certain sense, you might consider the dual notions. The tensor product, of course, is important in its own right. The tensor product is, well, one might consider it to be a solution to a universal mapping problem, just like the direct sum and the direct product work, with regard to something called bilinear maps, right? How many of you seen the tensor product before? Has anybody seen it in the linear algebra class? Has anybody had 8530 here? Do they do that in?
Yeah, or at least math it, or I took it like a couple of years ago.
Okay, right. So at least sometimes in 8530 they do tensor product. Do they do it over modules or do they do it over a vector space?
I think vector space. I think Michael Berg did when I took 8510 in fall of 2020. I think he briefly mentioned tensor products, like modding out by
Right.
like forcing it to behave the right way, but I think it was very weird.
Yeah, we're going to do some forcing here too about that. Yeah, and you can do tensor products in different categories, so
Yeah.
it's very natural that you might have done that. So even though it's not going to look like it at first, the tensor product, as I said, is infinitely related to Hom, and it's also a solution to the universal mapping theory. But the first mapping problem. But the first thing I have to do is talk about bilinear maps. Now, you can look in books where they do things a little bit more general. And when you take the tensor product, A tensor B of two modules, then you need A to be a right arm module and B to be a left arm module. And it's awful. I am going to assume it's a range of commutative. If you want to generalize it, it's not. I don't think it's especially difficult to generalize this, but it's incredibly tedious, right? And since I do commutative algebra for a living, I know I'm going to screw it up. So let's just assume that our rings are commutative here. The first thing I have to do is I have to tell you what a bilinear map is. And every time I explain this, I feel like I'm teaching Calc 3. Because what do you do in Calc 3, right? You do partial derivatives. How do you do partial derivatives if you have like f of x, y, z? If you want to take the partial with respect to x, what do? You pretend y and z are constants and you just do your business like you were in Calc 1, right? And if you want to take the partial with respect to y, you freeze x and z, they're constants now, and you do your business again. This is essentially the idea behind what we're going to call bilinear maps. So definition. This is sort of like somebody tried to take a homomorphism and add variables to it in a certain sense. So let's let A, B, and C be R modules. So I'm going to always assume this just to make my exposition easier. Let R be commutative identity. A, B, C are R modules. A bilinear map we'll call it F from A cross B to C is a function such that for all A, AI, and A, B, BI, and B, and R, we have. So what are my rules for bilinear function? One, F of A1 plus A2 comma B is F of A1 B plus F of A2. Two, F of A B1 plus B2 is F A B1 plus F A B2. And want this to F of A R B equals F of R A B is R F A. Okay, so this is a bilinear function. So it is a function sort of two variables, right? You have two inputs, two slots, one for A, one for B. Now, what this first equation says is it's just like Calc 3 again. If you freeze the B, it's linear in the first variable. So in other words, if B is fixed, this is basically an abelian group homomorphism in the first variable. And the same if you freeze the first variable. If you freeze A, then it's an abelian group homomorphism in the second. And this is kind of an R module thing. Basically, what this means is you can slide your constants through the different coordinates and out in front. All right. This is what we mean when we say a bilinear function or map. So, without further ado, let me define the set structure part of the tensor project. So definition. Here I'm going to let A and B be modules over R. Let A and B be modules over R, and let F free abelian group. Okay, what do I mean by that? Before I move on, catch you all up here, I hope. Okay, so A and B are modules, right? Now, just consider all ordered pairs. A comma B, where A is in A is B. Now, I'm thinking that only as a set right now, right? And F is just going to be the free abelian group on that set. What do I mean by that? That means that those elements sort of lose their relations, right? It's just a symbol, right? So, for example, if A is Z2 and B is Z3, well, I'll just do Z2 then A cross B consists of four things, right? Just there's your set A cross B in this particular case, right? And because I'm a very lazy person and don't want to write ordered pairs all the time, just for shortcut, I'm going to call this L1. Well, we call it Q1, P2, T3, P4. In this case, at this point up at the definition, F is the free abelian group on T1, T2, T3, T4. Where these are completely independent symbols. So a typical element of F looks like N1T1 plus N2T2 plus N3T3 plus N4T4, where the NIs are integers. And that representation is unique because this is a free abelian group, right? Just let the symbols run wild. It's just basically, so if you think about modules, if you think about this as this is basically a free Z module. This is just 4 copies of the integers so far, right? But of course, I'm not going to let the slowly go at that. To get the tensor product, what I'm going to do is I'm going to let K of F generated by elements of the form A1 plus A2 comma B minus B A B1 plus B2 minus AB1 minus AB2 and C so what you do is you collect every element of this free abelian group. Well, collect all elements of this form, right? And then see the subgroup they generate, right? So K is basically the smallest group that contains every element of these 3 forms, right? Of course, what I mean, let me make it clear, A1, A2, B1, A is an A, B, B1, B2 is in D, and R is in R. The quotient group F mod K is called the tensor product of A and B. Under the assumptions that we have, we've got a commutative ring of identities are all R modules. This quotient group is also an R module. Right, and we're assisted by that last relation there. Now, let me give you really good kind of some thought here. So, right, this is sort of mathematically the correct way to derive this thing. Oh my goodness, what a mess. I mean, you know, it's really hard to kind of wrap your head around what this quotient group is going to look like. You mod out, and this is called A tensor B. And this is, of course, an abelian group because it's a 3 abelian group mod a subgroup, but in fact, it's an R module. Let me make a note. A coset, because of course everything in A tensor B is a coset, because by definition it's an F mod K of the form AB plus K is called a tensor. And is written, and here's our notation, A comma B plus K is written A tensor. This is called a tensor. Sometimes I will say a single or an individual tensor. Note that not every element of A tensor B is necessarily a tensor. In fact, in general, so this, you might find this useful because I want to kind of give you my workaday thing. A general element of the tensor product is not necessarily an individual tensor. In some cases it is, but it's in fact a sum of tensors. A tensor B is a set of things that are sums of tensors. And of course, I don't really need that RI here because it can be absorbed. Notice that each RI can either multiply the AI or the BI, right, and be absorbed in there. But I do that kind of for emphasis. Subject to A, B, C from 6.82. So in particular, we have A1 plus A2 tensor B is A1 tensor B plus A2 tensor B. Because really what this relationship is saying, this relationship, since you mod it out, everything in the subgroup is 0 in the tensor product, which means A1 plus A2 tensor B is equal to A1 tensor B plus A2 tensor B. It also means this relation here, and so that's why you get this. So for example, A tensor B1 plus B2 is A tensor B1 plus A tensor B2. And R A tensor B is RA tensor B, which is the same thing as A tensor R. And that's why I pointed out that you can put this RI in either side of the point. So think about that. So as an exercise, think about that first where I took Z2 and Z2 and did their tensor product. See if you can figure out what that looks like when you play around with these relations. And we'll get to this next time. Any questions? Any questions? All right. Well, y'all have a good one, and we will see you on.